afternoon everyone. So today I am going to talk about the applications of Fourier transform. The last 2-3 lectures we have developed sufficient theory to look at some complex examples arising from engineering and sciences that can be solved analytically, mostly analytically or numerically otherwise as well, via the use of Fourier transform. So today I am going to talk about, so I will start with my applications of Fourier transforms to ordinary differential equations. From now on I am going to refer ordinary differential equations as ODEs. So consider the nth order ODE. So consider this nth order ODE. I can write my nth order ODE as follows. So it is an operator L which is acting on y, and L of y is equal to f of x, right. Let me denote it as 1, where my operator L is denoted by this following expression. So it is a n times d n plus a n minus 1 times d n minus 1 and so on. So this is plus a 1 d 1 plus a 0. So these are my differential operators. Okay. So I am talking about nth order linear ODE to begin with. So which means let us keep these coefficients as, let us say, constant or functions of independent variables. Okay. So in that case, if I were to apply the Fourier transform, so if I apply Fourier transform to 1 implying this equation that I have outlined here, I get the following algebraic equation. So I know that my operator L is a n. So instead of d n, notice that the Fourier transform of d n of f is reduced to an expression I k to the power n of f. So this derivation was done in an earlier, I k to the power n times Fourier transform of small f, and this expression was already deduced in one of my previous lectures. So my application of Fourier transform to 1 gives me the following expression. So I get a n I k n plus a n minus 1 I k n minus 1 and so on. I get a 1 I k plus a 0. Okay. So a 0, so that is my L operator, right. So from 1 I get this 1 prime, let us say. So my L operator is Fourier. So this is my Fourier transform of L operator. Okay. So I get the following expression now: a n I k to the power n plus a n minus 1 I k to the power n minus 1 and so on plus a 0 times the Fourier transform. Let us say the Fourier transform of y is capital Y of k, and the Fourier transform of f is, let us say, capital F of k. So I get Fourier transform of y is equal to Fourier transform of f. Okay. So in general, So, what I get is, so 1 prime can be written as follows. So, it is a product of two functions, the left hand side p of I k times y k equals f k, right. So, where this is a polynomial, it is a polynomial which looks as like follows. So, p k is a n I to the power k of n plus a n minus 1 I k to the power n minus 1 and so on. So, it is a polynomial of order n and the variable is k, or I can always invert this polynomial to get my solution in the Fourier plane. Y k is f k by p k. So, p of, let me say p of I k. So, then let us say that this is also equal to q k times f k, where my function q k is 1 over p of I k. Okay, so then my solution to the ODE, the solution to the ODE is given by y of x, which is also equal to the Fourier transform inverse of y k, which is nothing but Fourier inverse of q k times f k. So, then that will lead to the expression. So, we see that inside the argument of this inverse transform, I have a product of two Fourier transform, which means that in the physical plane this must be the convolution of the corresponding two function. So, when I take the inverse, I get the following expression. I get this is 1 by square root 2 pi, the convolution of small f with zeta times q of x minus zeta d zeta, okay, where q of x is the Fourier transform inverse, Fourier inverse of q of k. So, the final answer can be simplified from this convolution result. So, let us look at some examples. So, in electrical engineering, one of the common examples is to study the LR circuit. Okay. So, let us say I have the current in a circuit denoted by I of t, which has a resistance R and inductance L. So, the current satisfies the following ODE, which is given by L d I dt plus R of I is equal to some function, let us say E t. So, I am going to take my L and my R as constants to begin with. Okay, so, let us take, for the time being, let us take my forcing function E of t to be of the following simple form. So, this is E naught e to the power negative a mod t. So, this question says find I of t. So, to find the solution, notice that this is an first order ODE, right. So, once we apply the Fourier transform to this first order ODE, I get the following. I get that this is also equal to, so let us apply, so let me call this as, let us say 1 here. So, apply a Fourier transform to 1 and I get the following algebraic relation. I get I k times L plus r times I hat, where my I hat is the Fourier transform of I. Okay, so this is equal to the Fourier transform of E, the Fourier transform of E. So notice that the Fourier transform of E is of course the Fourier transform of this function E naught e to the power negative a mod t, and we have already discussed the solution to this function, which is given by E naught 2a divided by square root 2 pi k square plus a square. So using these known results, I am going to come to the solution to 2. I get that I hat, so from 2 I get my I hat to be E naught times 2a divided by square root 2 pi k square plus a square times this factor that we have got. So r plus I k l. Okay, so let us call this as 3. So now from this I can find the inverse of the Fourier transform. So the solution I of t is given by the inverse of the Fourier transform I hat, and this is also equal to the inverse transform of 2a E naught divided by square root 2 pi r plus I k l k square plus a square. Okay, and that will be given by 1 by square root 2 pi integral minus infinity to infinity 2a E naught by square root 2 pi times the two factors r plus I k l k square plus a square times e to the power I k t dk. Now, to find the solution we have to evaluate this integral. Now, to evaluate this integral we need some basics. I need to revise some basics of complex variables. So, let me just revise some complex variables basics. Okay. So, the two things that are important to find the solution to this integral, one of them is the Cauchy residue theorem. So, what is Cauchy residue theorem? It tells me the following. It tells me that if I have a function f z and f z is an analytic function, in the real on the real domain this could boil down to being differentiable, but in the complex plane analytic is a little bit more than differentiability. So, f x being analytic, then it tells me that the integral, the contour integral of f of z over a closed contour C divided by z minus z naught. So, this particular integral has a singularity at z equal to z naught, and the singularity is of the first order, also called as the pole. So, if I have the integration of the following function, then over the complex plane this is equal to 2 pi I f at z naught, or this is also equal to the so called 2 pi I times the residue of f at z naught. Okay. Then the next result that is important for us is the fact is that we want to integrate integrals of this form, minus infinity to infinity of the form f of k by g of k dk. So, notice that this integral is of this form, where over the complex plane. So, let me draw this. So, I am talking about a plane where I have the variables k being complex. So, on this plane the integral is from, let us say, minus infinity to infinity. So, let us say I denote a point r. So, from negative r to r, where r goes to infinity. So, this integral is also equal to the contour integral C of f k by g k dk. Now, what is this contour integral? The contour integral is, we have to draw a contour. So, let us draw let us say a semicircle, and the choice of this semicircle is due to the fact that one of the sides of this contour is our integral from in the limit r tending to infinity. So, we complete this curve to have a closed contour. So, C, so let me denote the circular part of this contour by CR. So, what I have is that, well, just to keep continuity, let me say that my variable of integration is z without loss of generality. So, anyway, z is a complex variable and so was k. So, let me say this is z and this is also z. So, in this range I have that this integral, which is over the real z or real axis, is equal to the contour integral minus the integral over the curved part, right. And further it can be shown that this integral goes to 0 under suitable conditions, which is given by the so called Jordan's lemma. Now, I am not going to go into details of Jordan's lemma. People can search up the basics of complex variables, and Jordan's lemma is quite available. Now, one important corollary out of this Jordan's lemma is that, especially if I have that f over g is such that the order of f, suppose f and g both are polynomials, and the order of f is 2 orders of magnitude less than the order of g, then this integral can be shown to be equal to 0 in the limit r tending to infinity, right. So, Jordan's lemma is much more than that, but we are going to use the fact that our fz is 2 orders of magnitude smaller than g and both are polynomials. So, coming back to our integral here. So, let us say this is my 4. So, coming back to 4, I have that I of t is equal to 1 by 2 pi, let me take out all the constants, 2a e naught integral negative infinity to infinity e to the power I k t divided by r plus I k l times k square plus a square dk. So, notice that if I were to take the absolute value of this integrand, then on the numerator I am going to get 1, and the order of the polynomial in the denominator will be 3. So, some conditions, so one of the conditions that the order of the numerator should be, the polynomial order of the numerator should be less than 2 or more than that of the denominator is quite satisfied. So, what I have is that this is also equal to, I am now going to use, so using my Jordan's lemma result, this integral boils down to 2 pi times 2a times E naught times 2 pi I times the residue of this integral at z equals, we can see that there are 3 roots of the denominator. So, I am going to take the residue at, well, in our case z is k. So, k equals I r by L. Again, let me draw the diagram here. So, I have real k, imaginary k here, and the contour I am talking about is the following. So, this is the integral, let us say this is the integral that I have from minus r to r, and this is my curve CR. So, I see that my k, let us say I denote this by k1. So, my k1 is somewhere here, and there is another root of this polynomial given by k equals IA. So, let us say k2 is somewhere here, and my k3 which is given by negative IA is given on the negative real axis. So, I do not have to count this root at all, because it is not inside this contour. So, finally, evaluating the residue, I get the following result. I get that this is equal to E naught times e to the power negative at divided by r minus al minus 2al e to the power negative r by lt r square minus a square l square, and that is my solution to the answer. Now, this was the case when t was positive. Well, if t is time, then t of course needs to be positive, but suppose t is a variable, an independent variable, we could also have t negative. So, in that case we have to calculate. So, let us say this is our integral 4. So, you have to find the residue. In this case, you have to find the residue at k equals k3, which is given by this value, to evaluate the integral 4 and avoid residue at k1 and k2, okay, because in that case the contour would be on the negative half of the plane, or the covering the negative imaginary axis when t is negative. So, all I have to do will be to evaluate the residue at k equal to k3, okay, for t equal to 0. And let me write down the answer. In that case, my IT, my current, becomes E naught e to the power at divided by al plus r. Okay, you can check that at t equal to 0, let me call this expression as b and this expression as a. So, at t equal to 0, you can check that for even for a or b, my I of 0 comes out to be the following constant. Whether you want to evaluate it from a or you want to evaluate it from b, it will come out to be the same. Okay. So, that completes my problem here. So, let us proceed to look at some more complicated examples.